It's like hello, hello. See.
Okay, hello, everyone can hear me? All right, I'm Lindsay Dougan from the Museum of Nature and Science, and I'm here to talk to you guys about how I am an accidental scientific illustrator. Next slide. Some of our illustrations. So this presentation is going to be pretty image heavy and video heavy. There are going to be some interactive bits towards the end if we can get there in time. Let's see. So yes, this is me, and these are the things I do in my job. Lots of different things that I've kind of built up over the years at the museum. But mostly what I do is digital preparation. So I use all these other tools in that main job. So exhibits have a lot of illustration in them. If you've ever been to the museum, you know that when you go through these exhibits, especially like Prehistoric Journey and the wildlife exhibits, we have so much art in the backgrounds there that are really setting the scenes for what you're seeing. What you don't know is that a lot of these images are actually taken from science. So we're providing illustrators with flora and fauna that they need to be illustrating, kind of helping them build this world. All of that stuff's been collected in paleontology from the field. And I just wanted to show this image on the right is my favorite illustration in the Teen Rex exhibit right now. It's Anzu, the hell chicken. It's beautiful, so pretty. Next. And in publications. So we do lots of stuff for outreach, in exhibits, creating all these images, but the main thing that we do is really create scientific images for publications. And so this is setting up really boring pictures that show anatomy or features, and then labeling them. This other image here kind of shows the work that we do between starting and finish. A lot of illustrated magazines will charge you for color, so we have to take scientific illustrations and turn them into grayscale, but it has to be kind of faked a little bit because we want to make sure those grayscale colors are really contrasted against each other. And I'll show you how we got this really contrast image later on in the presentation. Okay, so our lab's really special because we live inside the museum, we live inside the science division, and we mostly work in earth sciences. So that means we're looking at fossils, things that are no longer alive anymore and have probably been dead for millions of years. But because we're in-house, that means we get to work exclusively with our collections very closely. We get access to the curators and researchers who are doing this, and it also means that they have access to us whenever they feel like it. So if they have questions about how things are going, they want certain things set up a certain way, they can come straight to our lab and we can have these conversations. I would think that of all the museums in the country, we're kind of really unique in that. More and more places are starting to build these kinds of in-house laboratories, but we've been around for about 8 years, and so we kind of started it a little bit. Why CT? CT is non-invasive and non-destructive, so it means that we can look inside of these objects without actually opening them, which is how we can get endocasts, shapes of brains, soft tissue structures. If we wanted to do this on real specimens, we'd actually have to physically open them and create, traditional casts of those spaces. But with CT, we're able to look inside, and this is always a really great example. The specimen on the left here is an AMNH, American Museum of Natural History specimen. This is what it looks like when you get it from collections. It's been repaired. Bones that have been missing have been put back in there. And if you look at the image on the right, all of those gaps show where there's not actually bone. So looking at both of these are the same specimen, but one of them is showing us exactly what's really fossil, and the other one is showing us the reconstruction that was done sometime in the 1800s. The fun thing about this is the reconstructed specimen was what was used to describe this species, even though some of these elements are not real. So we re-described it and used the CT data to explain what's actually real fossil versus what's not. So it was a useful tool. Okay, so we do imaging and modeling. Imaging is usually CT, but we also do surface scanning. And then the modeling component is creating all of the images and media that you'll see. Lisa, those two images on the right are both videos. If you click on them, they're really short. We can see how we've kind of combined some of this data. And so that's actually losing all of the matrix that was around the specimen, and it is one of the ones up here that we looked at. That's what it looks like after you take all the rock matrix off, which is part of what our job is to remove all that stuff so we can see the fossils by themselves. And then up at the top, this is actually a combined video using surface data. So this was a surface scan. Now we have the CT data, and those little orange things that we see, those are actually the inner ear structures. So it's the cochlea and the semicircular canals. And those are really useful for determining maybe the environment and ecology of an animal. And also for this project, that was the first time we had ever modeled those structures in this animal. So yay to new science. You can go to the next one. Our basic workflow in the lab is scan things, segment them, study them, and share them. Sharing is probably the most fun part. Everything else is very tedious. But these images that we kind of create, these are really cool dynamic images that show three-dimensional things on top of 2D layers. So we're seeing what the data looks like, but also what the 3D models look like. And this is really useful for research and collaboration, but it also just creates some really interesting images that kind of engage people to ask more questions about what we're seeing and what we're doing. So for CT scanning, we don't usually use regular CT scanners. If anybody's ever had a CT scan done or done an MRI, you usually get in like a giant hollow machine, you kind of go through this tube. Our scanners are very different. These scanners are not clinical in any way, shape, or form. They will kill you very quickly if you get stuck in them. We're beaming like millions of volts into these fossils because they're rocks, they're dead, it doesn't matter, we're not gonna kill them by exposing them to intense amounts of radiation. But this image over here on the right side, that fossil is about this big. Comes up to my hip. We had to take it to Florida to be scanned in this giant scanner that is a whole room. That particular scanner, if you get stuck in it, you'll receive a fatal dose of radiation in 5 seconds. So they're really not messing around. They're pretty intense scanners. And these are all of the places that we work with. We don't have a scanner at the museum, but it means that we get to make these really great collaborative relationships with people who have scanners and are really interested in the things that we're working on. Okay, this is also a video. You can play this one because it's a bit long. So this is actually a demonstration of like what our normal day-to-day work looks like. In the bottom, you can see my hand on our pad. I am painting these different elements. What we're looking at right now, hard to tell, teeth, mammal teeth. And I'm painting out the roots right now. Mammal teeth are really important because they're super diagnostic. Different mammals have different tooth shapes, and those teeth shapes tell us a lot about what they were eating. And so looking at the shapes of teeth is really important for mammals, making sure that we get all of the tooth elements, so when we create that 3D model, we know exactly what these bumps are. If they're real bumps, fake bumps, did the tooth crack, can we put it back together? And sometimes those hollow spaces that we see in teeth are actually where nerves would have gone in to innervate those teeth, so we can actually see how many nerves are kind of going into those teeth. Those places should all be preserved if the fossil preserved really well. And you can see the blue and the pink are both molar teeth. This is a really weird way to look at it because it's an oblique cross section. So it's not on an anatomical plane. This fossil is kind of warped a little bit. So even though it has two sides of teeth, they're really funky. So they kind of cross strange when we're looking at it. So you have to use weird visuospatial skills to kind of understand what you're seeing and look for these different patterns of blacks and whites and just textures is the best way to describe it. And when we're looking at these images, we're also looking at the density values. So the brighter an element is, the more dense it is. Hopefully all of our bones are showing up really, really bright and really dense. Softer, less dense material is gonna be darker. So air should technically be black, and that's kind of the boundary that we use. We're kind of looking to isolate these really bright bones because that's what we're interested in, is the bones that are fossil bones, not rock fossils. So you can move ahead. Skipping through the videos is tricky sometimes. Ooh, yeah, let's advance, because I think I have a 3D render so y'all can actually see the teeth instead of just looking at weird cross sections of them. Yeah, that's okay. This is another video to show segmentation process. So the things that we're doing You can see up here the numbers that are listed. This is 2019 image slices for an object that's about this big. So the resolution's really high, and that's why we can see so much detail. The red color is a cranial bone, the green color is another cranial bone, and those blue elements, those are actually spaces that would make up the semicircular canals in this animal. This is 250 million year old reptile relative. I don't know that it has any living relatives now. I think they're all extinct. But this one's really important for determining the lineage of turtles. So we're looking at the inner ears and the bones around the inner ears to kind of see where this animal falls in the family tree of turtles and other reptiles. So up in the white corner up there, the blue is the actual 3D render of that structure. So we're going slice by slice, painting this all together, and the software is actually stitching each of those slices into a three-dimensional model. So we go back and forth between looking at 2D and painting, looking at it in 3D, making sure we're on the right track, that everything kind of makes sense. If we have questions, collaborate with our collaborators. Ask them, does this look like what you expected it to look like? Do these measurements seem right? Should we look at it again? Very complicated, as you can see in this image. It's not ideal. There's a lot of really bright stuff in there. This particular specimen has a lot of pyrite in it. So it's very bright, it's very dense, and lucky for us, maybe sometimes, it actually filled in spaces inside all of the bones. So the kind of messy stuff that you see, that's actually the hollow bone, the trabecular bone inside of these cranial bones. So this stuff leached into those spaces, and it made it really challenging to segment, but it did help us know that there's actually fossil here. So we were using that kind of as a reverse image search, looking for darker and brighter in a different way than we usually do. Okay, so the study part. These are actually images from an active research project that we're working on. The color-coded is the photo of the fossil from the top down, and then these different elements are kind of color-coded around it. These are the ones that we've isolated in varying stages. So we have a fully articulated foot here. There's the femur, that pelvis, that 3D print's actually down here on the table, and the blue one is the pelvis. And these are all pieces that we were really interested in isolating to determine what animal they came from, if we can find out how old they are. They're definitely mammal. We know that they're not crocodile, but we don't actually have an age yet. So this project is still in progress. And this was our most recent data set. This is actually a little chunk. It's about this big. And when you look at it, it has a lot of fossils on the surface. That's a really nice croc jaw. And this is actually what we sent to Florida when we were working with it. This is part of that. Each one of those colors is an identified bony element, and most of the stuff in this section is from a crocodile. So we've got a lot of these little bones that are called osteoderms, that are basically little armor bones. We've got a lot of vertebrae, we have long bones, that really nice jaw, all kinds of weird stuff in here. We're still sorting through what all is in here. So we're in the process of doing the inventory for this, but also the giant section that goes with it. Right now we're anticipating close to 300 different elements from both of those sections. And this took about 2 weeks to process from start to finish. And this was done by our current intern, Tara Hobbs, who's been with us for about a month. Oh no, these are the fun interactive models that if you look at the QR codes, they will load on your phone. But these are different ways that we can share the data. So what these are actually three-dimensional models that are hosted online that users can interact with on their phones. Some of them are labeled, so they have annotations, so you know what you're looking at. If it's a 2D image stack, which are the next slide has those QR codes, you can actually move through the image stack, see the data that we work with, and then switch it to a 3D render where it will show you those objects in 3D space, and you can kind of manipulate them very similarly to how we do it in our lab. These are really easy to share because they come with QR codes when you have the add-in in there. Sorry, I forgot about that. But they're really neat. They're all things that we've made in our lab. It makes it really easy for us to share with people because most of the files we have are gigantic, and sharing them on here means they have to be really compressed. So they still keep a lot of their surface data, but it means that it's a much more deliverable package for people to access and use. So we can skip to the next one. It's going to look the same. But these are all the CT scans, and there should be limb bones, a spider, and mummies. And so those QR codes link to those. The spider is incredible. I've never seen the inside of a spider before. I don't know if any of y'all have ever seen the spider anatomy. It's remarkable. So cool. When you turn it into 3D, it's a little scary because it's a spider face staring at you. So perfect for Halloween. Also, the mummies are perfect for Halloween. The mummies are great. This is one of the mummies that's on display, and I love this scan because it's preserved the musculoskeletal system of this mummy so beautifully. You can see all of the muscles where they should be, all of the bones are there. You can just see so much anatomy preserved, and it's really remarkable that, you know, these are thousands of year old mummies that still preserve so well, and they look so beautiful. Yeah. So you can skip now. And this is the surface scanning software that we use. We use Artex scanners, and we use Artex Studio. So this is kind of what the interface looks like. That model right there is the Teen Rex model, so I have some down here as well. This is our scan to mesh modeling software. We scan something, it creates a mesh almost instantly. This is so fast and so great. The thing that we use it the most for is actually generating these photorealistic textures that we can put on these models. So we can show something that looks like a real fossil and then show you all of the anatomy that we've pulled out of it in another view. So we're combining these to create really cool, beautiful kind of figures and animations. And this is a video. We don't have to watch the whole thing, but this is how we scan stuff. So this is us actually scanning the Teen Rex block. You can see how giant it is. It has a T-Rex in it, so it is pretty large. This T-Rex was probably about 13 years old when it died, so it's not full grown, but it's very, very big. And these students that I'm working with are teen science scholars. We had 2 teen science scholars. One was going to be a junior this year and one is a senior. They came and spent 6 weeks in our lab and learned everything that we do, but this was one of our favorite activities, scanning the specimen. So she's using our Leo scanner right here, and what you can't see is there's actually a computer built into this, so as she's scanning, it's building the model and she can see what she's creating with that scanner. Just going over the object very slow for a very long time. And this is the exhibit. So if you come to the museum, this is actually an exhibit room. You can come and talk to the preparators. Tuesdays and Wednesdays, my lab is in there usually surface scanning stuff, so people can come ask questions specifically about that or specifically about the fossil. I will preface, I don't know anything about dinosaurs. Yes? How big? Oh my gosh, that's a really good question. Giant. How old? So they fully mature, I want to say, after they're like 15. So this one's pretty close, but this is a question that we're trying to answer. Most of the T-Rex specimens we have are either definitely adult. We have a couple that are really young, but we don't have many that fit in that middle range. And so what we did for this one was actually take measurements from the long bones. We have the femur and the knee joint, so we actually did measurements to compare it with other known T-Rex specimens to estimate where it would fall in body size with those. And then the other thing that we have is these bones are all skeletally mature, so they don't have the growth line on them that indicates they're still growing. So we know that this one it's skeletally mature, it stopped growing, but it's not quite fully an adult yet. It's hard to tell when they get sexually mature because it's really hard to sex bones in dinosaurs when you only have like 12 of them. And some of those things don't get preserved in the specimens. So this one's pretty large, but it's still not the biggest. I think the biggest is Sue in Chicago. Giant. You could live inside her rib cage, basically. Pretty big. Okay, and then these are the 2 scanners that we have. the Leo, which is our large object scanner. It's an untethered scanner, so this is also one that we can take to the field. This has been to Peru to surface scan murals and things inside of temples that have been uncovered with our archaeology team. So it's a really great tool for preservation. Things that we know we're not going to be able to have exactly as they are for a long time, which is why we're scanning the Teen Rex block, but also the archaeology team is using this when they go out every summer to kind of record the new things that they're finding. Our tiny one is actually a small to medium scanner, the Space Spider, and this one is our high detail capture scanner. So this one has, I think, twice the capability resolution as our Leo, so we can scan smaller objects. Unfortunately, this one is a tethered scanner, so this one's not good to take out into the field, but it is still somewhat portable. So we take it all around the museum. That's really all we take it, just different places in the museum to scan different objects. Everything that we're scanning, as long as it's something that's been published, we're hosting online so people can access this data because these collections are really cool. We want people to look at them. Even if you just log in to visualize it, that's still pretty awesome. Just getting to see lemur bones. All right, and this is, I think this is also a video. But this is the most recent model of the T-Rex from the 2nd of October, so it's only a couple of days old. But this is the final product, so you can kind of see the detail that it's captured. That's the scale bar. We have brushes. There's a toothbrush up in the corner up there that you can actually see what's on the toothbrush. It captures great resolution for such a large object. So the things that we're looking at in here, sending it to different collaborators. The palm frond is potentially the oldest, largest palm frond from this time period. So that's been really exciting for the paleobotanist people. And one really cool thing that you can kind of see on this, the stalk of the palm actually has teeth on it still. So if you've ever seen a real palm tree and looked at where those fronds are coming off, that stalk's really sharp and it has all these teeth. They're preserved in this specimen, and that was also a surprise. So it's a really toothy block. It's got a lot of teeth in it. All right, so the last thing I'm gonna cover, I think, is Blender, which is our animation and figuring studio software. It's very similar to any kind of animation software that you would use, Maya or whatever Pixar uses, RenderMan or something like that. But we set up all of our models in here. We use the camera to actually capture these really high quality images because publications have such rigorous standards for reprints and things. So we can export like 600 DPI images from Blender using all these colors. It can be all different file formats, and it also does movies. So we can do still shots from animations, we can just do still shots, or we can just do animations. I would say between all the software that we use, our segmentation software and Blender are the two that we use the most, because we also use Blender to post-process our models, so make them just prettier, more attractive looking, not as rough, smoother, so they look more like the bones that we think they are. And it's free, it's open source. Everyone can use it. Oh yeah, so here's our figures. All of these were created in Blender. This first one is that color test to generate kind of really high contrast images. When we were talking through with our researcher, we thought maybe we'll do a color image with just one color because that's cheaper than 3 colors. But we eventually decided on going with grayscale, but that meant that we had to really kind of force contrast into this grayscale edition by creating these really different color backgrounds and then converting it to a grayscale image. And then the bottom is actually testing different lighting. So Blender is great because you can add lots of lights, different kinds of light sources. This is really useful for actually giving relief to your models. They're all 3-dimensional. Without the light, you kind of lose that relationship though. So the lighting and the shadows are really important for getting across. This is a 3-dimensional object that has texture and it has crevices and smooth places. And these are all different tests that I sent to our collaborator to decide what he wanted it to look like in the final publication. And then over on the right, that's our Lucy layout. This is anatomical kind of modeling of all of the bones we found for these 2 individuals in one of our blocks. And so doing the inventory process, all the little stuff at the bottom, those are all teeny tiny bones that are really hard to identify. Things like carpal bones or foot bones or osteoderms, because they're alligators and crocodiles. And so we've tried to place them in their anatomical position. And for this time period, these are 64 million years old. Those are pretty complete. That's pretty good for fossils. So we're pretty happy with that, those two crocodiles. And this is one of the animations. This was made by a former intern, former staffer, Franklin Duffy. This video is a reconstruction video. So this is one that we create with a lot of the models that we have, putting things back together, trying to show the motions that these bones would have had, joints, teeth. Every single color in there is a different bone of the skull. So we did a bone-by-bone segmentation of this, looking at all the bones that are in here and kind of thinking about how they fit together when this animal was alive. This one's also from Corral Bluffs. This is Ectoconus, probably coyote-sized. The one we have up here is kind of small, but they range in size. These are pretty big mammals for the time period, though. Probably not one you'd want to fight. Had pretty big canines. And these are some other reconstructions from the same project. So these are how the bones were when we pulled them out of the block. And then this is our hypothesis for how they fit together. So this is a foot. That really long green bone back there is the calcaneus, so your heel bone. When you touch your heel, that's the bone that you're feeling. This one is the articulated limb. We have tibia, fibula, all of the feet, the same foot in both of those, but we're kind of fixing those bones back from how they got twisted when this animal died, putting them back into their correct anatomical position. And all of these are things that we send to our collaborators saying, like, did the bones get put in the right place? Did we assign the calcaneus correctly, or did we accidentally mark a different bone? So these are actually still in progress because there are some tweaks to make after we sent these videos off, but it's a really cool process to sit and redo all of these weird biological puzzles. Exploded skulls. Is anybody familiar with the exploded skull model? It's very cool. Basically, again, bone-by-bone segmentation. Each color is a different bone. There's a lot of bilateral symmetry in crania. So for this one, what we did was identify all of them, separate them out, look at each bone individually, and then fit it back together to reconstruct what it would have been like in life and fix all of that deformation from being fossilized. So very tedious process. Involves so much 3D printing of giant bones because this skeleton is like the size of my thumb. It's really tiny. And so we had to print them really large so we could actually manipulate them and see how all of these bones fuse together, what those joints look like, and then take that knowledge and do the same thing again digitally. So it's a pretty slow process, but it yields really great results. And it's super helpful for anybody that wants to be working on this project and wants to know about these bones and the animal that they belong to. And this is another one from 250 million years ago. Fun fact about this one, I've never seen this physical specimen. I have only ever worked on the digital data. It doesn't belong to us, it belongs to South Africa, but we've done all of this work using just CT scans. So this is another really useful tool in science. You can scan a specimen and work on it and not have the specimen with you and still get so much data from it. The last thing I'm going to talk about, I think, for Blender is rigging. I don't know if any of you guys are animators, but rigging is really hard. This video is very silly, and it took me 3 weeks to make, and it doesn't move very much. But rigging is basically how you animate motion inside animated videos. So the rigging feature is, oh, I hope it moves. Maybe it doesn't. Oh, maybe it's broken. It's possible. Well, all it does is move its hands and turn its head, and it took 3 weeks. So rigging is really challenging, but it can get you some good results if you have patience. This is how animations are. There's a whole rigging setup inside of Pixar that just does the rigging, and then there's another setup that does the movement of the rigging. So you're basically creating this rig structure that is a skeleton for your character or your model. It doesn't quite match a real skeleton because that can get really complicated, but you need to have them in the joints that you're going to be moving. And so this is something, if you've not done it before, it probably takes several iterations. I think remembering where all the joints should be is the first challenge of setting up your rigging, and then actually getting those motions to look smooth is the second challenge. So all around, creating motion animations is very challenging and not something that we do often. This was a special request, and I haven't done one since. This is a Dolotherium, crazy beast from Madagascar. So that one was also alive with dinosaurs. And this is our 3D printer. Its name is Lenient Dingo. That's the name the company gave it, and that's just what we kept. But it's a pretty large 3D printer. It's an SLA printer, so it prints with resin, and it uses UV lights to cure into the shape that we're printing. And it prints at really high resolution. I think we can go down to like 25 micron layers with this. And for reference, most of our data sets don't even have that high of resolution, so the printer could print higher than we actually are capable of generating models for. So it's a great one to have in the lab. We maintain it. Everyone in the lab knows how to use it. Everyone's responsible for keeping it clean, making sure that we're actually printing things with it. And that's why we have all of this stuff down here, is because we print a lot of things most of the time. We're printing something. And I think the next slide has a video. Oh no, this one's really fun. I have the brains up here. So this is kind of the process. This is what it looks like when we set up a printer. We have our build platform. Most printing software is the same. It's very similar. You're going to take your model and set it up. This is a little tricky. Sometimes really complicated models don't like to be set up a certain way. So this can take anywhere from 5 to 20 minutes to get something set up. Sometimes it can take longer if it's a really complex process. When they come off, we wash them. So up there, the brain was hollow, so it floated. It wouldn't go into the water. Actually, that's alcohol. So we wash it with alcohol and then throw it in our tanning bed to cure it. So this is just a small UV chamber that adds extra UV exposure to this to kind of do the final cure on it, so that way it stays extra hard. If you don't cure it after, sometimes those layers can kind of rub off with too much use. So curing it makes them much sturdier. And it also looks like a club for things. It's fun. And then the other picture was these brains took forever to make, and I was really happy that they finally worked. So that was right before I was about to wash it. They're really gross when they come off the printer because they're so sticky and slimy, and that's why we have to wash them. Then they get nice, and people will touch them. You don't want to touch it after it comes off the printer. It's yucky. Oh yeah, so this is actually the exploded skull specimen, one of our test prints for the reconstruction of the skull. Giant size, and then the one over in the corner, that's the actual size of the specimen, so it's pretty tiny. We always make them really big because then you can actually see what's going on. These are pieces that we use in our lab with our researchers, fitting pieces together, making sure that their jaws actually close, those kinds of things. And also, they become fossils you can touch after we're done with the research process. And so this is what it looks like when we set up for events and bring all of our 3D prints out for people to touch. I think the right side is a video, but it is just a video slow-mo of this cool table that we have set up. This was our display for the Teen Rex opening, and we have so many models that we've printed, a lot of stuff that our teen science scholars were working on, a lot of the art that goes with these different projects. Most of the art actually on this table was done by the same artist, Andrea Tuchin, and actually this dinosaur face was done by intern Joel, who's also an artist. So he drew the rest of the skull that goes with that lower jaw so that people can have a reference point for what element of the skull that bone is. Yeah, and we brought out our TV to show some videos. Let's see. And that's it. That's all I have for you guys. Sorry that the interactive models didn't work. That's always a bummer, but we have other things you can check us out. Obviously, our website, if you have questions, you can send me an email. And we have 2 different Instagram accounts. If you want to follow one, definitely follow Jurassic Giants. They're the super fun one, and it's run by Prep Lab people, so they are showing you the things that they're working on. And sometimes we get put on there too. But yeah. You're welcome. Sorry I was late and there was computer problems. That's normal for me.